The last electron configuration we looked at was vanadium, and we saw that there were 2 electrons in the 4s and then 3 electrons in the 3d. After vanadium on the periodic table comes chromium. You would expect that that extra electron for chromium would fill into the 3d orbital, giving you 4s2, 3d4 for chromium. However, that's not what happens. So this 3d4, 4s2 for chromium, which is what you would expect looking at vanadium, is not actually what happens. And instead of having those 6 outer shell electrons arranged in a 4-2 split, they actually rearrange to give you a 5-1 split, with the 4s orbital now only having 1 electron. And the reason that you get this exception to your rule is because 3d5 and 4s1, we know that d orbitals can hold 10 electrons in total because there are 5 of them. So having 3d5 means that it is half full. And we know that a 4s orbital can hold 2 electrons. So having 4s1 also makes your s orbital half full. And having 2 half-full orbitals, a 4s1 and a 3d5, is more stable than having a full s orbital and then 4 electrons in your d orbital. So instead of having this 4-2 arrangement, the electrons rearrange to give you a 5-1 arrangement. And this is an exception to the rule, and it's one you have to know. Okay, chromium, 3d5, 4s1. If you continue on for chromium, everything else is as expected. So chromium, we said here, was 3d5, 4s1. When you move on to manganese, it goes to 3d5, 4s2. So that s orbital becomes full again. Then you move into iron, you're going to have 3d6, 4s2. Okay, cobalt is going to be 3d7, 4s2. Nickel is going to be 3d8, 4s2. Okay, so all of those electrons are just filling into your d orbitals. Okay, but again, we get to copper and we have another exception. Nickel's 3d8, 4s2. You would expect copper to be 3d9, 4s2. Okay, you would expect copper to be 3d9, 4s2, but it's not. Okay, for the same reason as chromium above. Instead of having those 11 electrons in a 9-2 split, those electrons rearrange to give you a 10-1 split. Okay, and again, the reason being, with this 10-1 split, you have a half full s orbital, which is relatively stable, and you've got a full 3d orbital, which is stable. Okay, so rather than having a full s and an almost full 3d, it rearranges to give you a half full s and a full 3d. Chromium and copper are your exceptions, okay? You need to know them. They don't follow exactly the same pattern as the other elements, and you need to be aware of them and be able to write out their electron configuration. In our definition for orbitals that we encountered earlier on, we saw that electrons only occupy orbitals if they have opposite spin. Now, we've never come across spin before when we've been talking about electrons. It's a different property that electrons have, and you don't need to know anything about it. You just need to know that this property exists and that electrons can either spin up or they can spin down. In order to occupy an orbital together, electrons must have opposite spin. So if we look at all of the diagrams I've been drawing in these videos, you'll notice that the way I'm representing electrons is I have one arrow pointing up and one arrow pointing down. Okay, and I haven't explained that until now, but the reason I'm drawing one arrow pointing up is to represent spin up, and the arrow pointing down represents spin down. And you will notice that in every single orbital that I've filled, I never have 2 arrows pointing up together or 2 arrows pointing down together. When I fill them in, they always have opposite spin. That's simply represented as 1 arrow up, 1 arrow down. That's all you need to know about spin. Okay, you don't need to be able to explain it. You just need to know that when you're putting them in the orbitals together, 1 electron is spin up, 1 is spin down, and you represent that by using arrows pointing in different directions. And the commonly way that they assess this or ask this question is they'll give you this, what's called the electron in box model. And I've drawn out boxes to represent each of the orbitals, but what you'll notice if I put all of the boxes on the same level. So I haven't told you in this diagram that the 2s is higher in energy than the 1s, or that the 2p is higher in energy. Okay, they're all just drawn on the same level, and you're expected to know which are the highest in energy. And what you'd be asked to do is, for nitrogen, you'd be asked to complete the electron in box model. Okay, so I'm going to start off. I know that the 1s orbital is the lowest in energy, so I know it's going to fill first. So I'm going to put my first electron, and then I'm going to put in my second electron. I don't move on to 2s until 1s is full, and I need to show that they've got opposite spins, so I've got 1 arrow up and 1 arrow down. Then I move into my 2s orbital. I've got 1 arrow up and I've got 1 arrow down, and I completely fill 2s before moving into 2p because 2s is lower in energy. I've assigned 4 electrons, I've got another 3 to go. And because I know electrons occupy orbitals singly before in pairs, I put 1 electron in 2px, 1 in 2py, and 1 in 2pz. I do not fill 2px before moving to 2py. Okay, remember, electrons are negatively charged, they repel each other, and if you have available orbitals that are all of the same energy, they will fill singly before filling in pairs. If I were to do the same for fluorine, fluorine's got 9 electrons, okay, I'm going to fill 1s first, then I'm going to fill my 2s orbital, then I'm going to move on to my 2p. I've assigned 4, I've got 5 to go, so I'm going to go 1, 2, 3, and then back for 4 and for 5. Okay, I fill them singly, and then I go back and I fill them in pairs. Now, when you're drawing your electrons in, it doesn't matter if you do spin down first. I always, as a habit, just do spin up first. It doesn't matter. As long as you have got opposite spins in the same box, then you are fine. And as long as you fill singly before going back and filling them in pairs, you are fine. Okay, so what I've just gone through is all covered in your notes. At the end of page 6, you've got the exceptions, chromium and copper. And at the top of page 7, you've got the opposite spins. And I have some examples of electron in boxes, what's acceptable, what's not. Underneath at the bottom of page 7, you will see blocks of the periodic table. This is just how your orbital model ties back in with your periodic table. And it says that your periodic table can be divided into blocks. So if I look at my periodic table, group 1 and group 2 can be called the S block. And the reason it can be called the S block is you will see that all of your group 1 and group 2 metals have their highest energy electron in an s orbital. So if I look at lithium, when I draw out the electron configuration for lithium, I see the highest energy orbital is a 2s orbital. For calcium, the highest energy orbital is a 4s orbital. And you will see that for all of the group 1 and all of the group 2 metals, when you write out the electron configuration, their highest energy orbital is always an s orbital. So we call them the s block. If I go to my periodic table again, I can call groups 3 to 0 the p block elements for the same reason. If I write out the electron configuration of any of my group 3, 4, 5, 6, 7, or 0 elements, I will see that their highest energy orbital is always a p orbital. And I've done that here, okay? If I draw out carbon, highest energy orbital is a 2p. For bromine, the highest is a 4p. Okay, so you're always going to have that last electron filling into a p orbital. And then if you have got your transition metals, okay, transition metals, this group here, are also called the D block elements. The reason they're called the D block is, again, because their highest available, their highest energy orbital is always a d orbital, okay? And their last electron will fill into that d orbital, making them the D block elements. The last thing we need to look at is how to write the electron configuration of ions, okay? If I look back at the example I did out for sodium, sodium is in group 1. It's going to lose one electron when it forms an ion. And when it loses an electron, that electron is going to come out of the highest filled orbital. So if I were writing the electron configuration for a sodium ion, I would write it exactly as I had before, but it's now got one less electron and it doesn't have a 3s electron anymore. If I was doing it for aluminium, aluminium's in group 3. It's going to lose 3 electrons and it's going to lose those electrons from the highest energy orbitals. So I'm going to be left with my 1s2, my 2s2, and my 2p6, and I no longer have 3s2 and 3p1. If I were to look at something like phosphorus, which is a non-metal means it's going to gain electrons. It's in group 5, so it's going to gain 3 electrons and give me p3 minus. And if I were to write the electron configuration for that, those electrons are going to fill in to your highest available energy level. So I'm going to have 3s2, and then I'm going to have 3p6, which will give me a full outer shell for phosphorus. If I was to do the same for chlorine, chlorine's in group 1, so it's going to have a -1 charge. It's going to gain 1 electron, and that electron is going to go into the available 3p orbital, giving me 3s2 and 3p6. So you'll notice that when I write the electron configuration for all of these ions, it matches a noble gas. Okay, sodium now has a full outer shell, aluminium has a full outer shell, phosphorus and chloride ions also have their full 3 energy level, giving them also a full outer shell. With the transition metals, they're all metals, they're all going to lose electrons when they form ions, okay? And we saw when we were filling the electrons in for transition metals, and I've got vanadium done over here, we know that the 4s is lower in energy than the 3d, so the 4s fills first, and then you put the electrons into the 3d. However, when the orbitals are actually full, the 3d orbitals become lower in energy than the 4s when the 3d is full. Okay, so when they're empty, 4s is lower, which is why it fills first. But when they're all full, the 3d becomes lower than the 4s. That means when I've got them filled over here, as I do for scandium, when I've got them full, the 4s now becomes the highest energy level. And when I'm forming an ion from scandium, I'm taking electrons from the 4s. I'm not taking it from the 3d. So the 3d fills last, but the 4s will empty first. So if I was doing scandium, and you'll be told what charge is on the ion because transition elements can form lots of different ions. If I was forming Sc+, I'd be losing 1 electron. Yes, the 3d fills last, but it's the 4s that will empty first. 4s becomes higher in energy than 3d when they are full. If I was doing titanium, so I was doing titanium 2+, the 3d fills last, but the 4s will empty first, and you will get 3d2 and 4s0. If I was doing vanadium, I'm going to do a +1. Remember, there's lots of different ions that these transition elements can form. 3d fills last, but the 4s will empty first, and you'll have 3d3, 4s1. Okay, so a little bit confusing potentially. Okay, yes, when you are filling, 3d is higher in energy than 4s, so 3d fills last, but when they are full, 3d becomes lower in energy than 4s, leaving the 4s as the highest energy orbital, meaning when you are forming ions, the electrons are coming out of the 4s before they're coming out of the 3d. That is the main reason why it helps to write your electron configuration with the 3d first and then the 4s, because when you're writing the ions, then it's easy to see which orbital you're taking your electrons out of. That's pretty much all of 5.1. I know there is a lot in it. I would advise doing exercise 3 and just writing the electron configuration of some ions, and then moving on to exercise 4 and doing all of those practice questions. In the next video, I'm going to go through the answers to all of exercise 3 and all of exercise 4. So if you do it by yourself first, and then look at the next video for answers to the questions.